So, um, making a video on comparing two means. And the example that I'm going to give you is going to be based on a two-sample t-test, T as in Terry, not a two-sample z-test, Z as in Z. Two-sample means comparison, and let me just point this out. If you have the sample standard deviations, you will use the two-sample t-test. And an aside here, even if you just had one of the two standard deviations being a sample standard deviation, you would run the t-test. You have to have both population standard deviations in order to be able to run the two-sample z-test. Now, there's this degrees of freedom issue that exists. And so the first degrees of freedom would be if the variances are considered equal, and the degrees of freedom we use would be the sample size of the first sample, the sample size of the second sample minus 2. That's if the variances are equal, and we call it pooled. And we're not talking about the variances that you're looking at in the sample. You're assuming the population variances, because a sample can be different than the actual population. Your values might be slightly off. And if the variances are considered not equal, it's called not pooled. And then there's this really kind of convoluted formula here. And we don't use that. There's a simple way. Generally, when we're in introductory stats course, what we do to simplify things, because quite frankly this thing is a calculator nightmare, what we do is we take the sample size that is the smallest of the two sample sizes and subtract 1, and we use that as our degrees of freedom. That simplifies matters, and we don't get hung up and lost in what we have to do there. If you do feel brave and daring and you have to type this in, take a screenshot of it and have it as the formula. I do seem to recall somewhere on Alex that it asks for the formula typed in once, but hopefully I was able to pull that out of the homework set. Forgive me. All right, so I've tried to pick just an example problem. There was a claim made that the mean height of men is greater than the mean height of women. Okay, so null hypothesis here. So when you have two samples and you're comparing two means, you're going to be talking about, and again, you have the same relationships: equals, not equals, greater than or equal to with less than or equal to with greater than. We have this claim that's going on that the height of men is greater than the mean height of women. That's going to land in the alternative hypothesis. So the mean height of men is greater than the mean height of women. And the reason is because this is a strictly greater than symbol. Right here is strictly greater than. It is not greater than or equal to. Its counterpart is that it's going to have less than or equal to. So the mean height of men is less than or equal to the mean height of women. Now again, I know that I've said this before, but you can have that just be strictly equal. So that piece could be just an equals. So we've established our null and our alternative. Our claim is actually associated with the alternative hypothesis. And we're now going to generate our distribution, and we're going to try and find our critical value. This is going to give us a right tail test because the arrow is off to the right. We're going to shade this region. This is our reject the null region. Here's our 0. And this is our fail to reject the null region. Now here's where it gets a little bit more challenging, because before this 0, that t-score represented a value represented the value in the null hypothesis. Here, that 0 is representing, is there enough of a difference between the two values to cause us to have concern? In other words, we're now looking at taking the two samples and seeing, are they too far apart or are they very close together? So if they're too far apart, our test statistic is going to land in this rejection region. But if they're fairly close, then they're going to land in this failed to reject region. Now, that's a statistical idea, and it's partly tied into our standard deviation. So I'm going to go up here, put a little, give me a second here, sort of give you the idea. So in both instances, why is that not letting me draw? There it goes. It's still not letting me draw. What's going on is we have two distributions. So the men's value it's got a mean here, and the women's value has a mean here. And you have two distributions based on the standard deviations from the sample. And you're putting that distribution over this distribution. And basically what's happening is based on the standard deviation, is this mean here and this mean here inside that basically 1.96 and 1.96. So within two standard deviations of each other's distributions. So is this mean inside this thing's two standard deviations? Simultaneously, is this mean inside the two standard deviations of this distribution? Now, it would be much, much easier to tell what I'm saying is if I did the following. Suppose we had this happen. The mean is way over here, and here is our distribution. Notice this mean is not inside the two standard deviations generated by this distribution. And this mean is not inside the two standard deviations of this distribution. And then they clearly are statistically different in that case. So we have this defining line created by a critical value that says if they're far enough apart or not. And so that's what we're working to get to. Now, let me go back to here. Let me go here, because I probably messed up some stuff by doing what I did. Good, now we're back to having our null and our alternative. Okay, now we've got the fact that we are assuming that the populations, our variances are equal. So that means that they are pooled, and we're going to take the sample sizes of both of them and add them and then subtract 2. So we have 25 men and 25 women in our sample. So we have 25 and 25. What we're going to do is add those, and we're going to get 50, and then we're going to subtract 2. So our degrees of freedom will be 48. And I picked that value again. So our degrees of freedom are 48. Let me go back to the table that we had up here before. Where'd that go? My table left me. Well, let me just go to INVT. Forgive me for using the table. I don't know where I put it, but I must have clicked it off mistakenly. So clear that. Second vars, INVT. The area, well, notice our problem doesn't have a stated level of significance. So the level of significance that we're going to use here is alphas equal to 0.05. Now I'm going to do INVT 0.05, degrees of freedom of 48. I'm going to go ahead and hit paste, hit enter, and I get that negative 1.67. Now notice this is to the right side, so what I do is I just change it to 1.67 because the distributions are balanced, or symmetric, forgive me. So next thing we need to do is we need to get our test statistic. So I'm going to do this. I've got men, I've got women. Our sample sizes are both 25. All right, so now we need to get our x bar and our s sub x, our sample standard deviations. They were both 2. This one was 2, and this was in 2. And these are both in inches, I believe. I said 2 inches? Yep. So the problem is units at this point in time. So I have 5 feet 7 inches, and I have 5 feet 6 inches. So I need to convert that all to inches. So my units need to be matching. So 5 feet, so 5 times 12, there's 12 inches in a foot. So I have 60 inches. So for men, it was 67 inches. And for women, it was 66 inches. Now, go to Stat, go to Tests, and find 2 sample t-test. It's number 4. Now, again, Stat, not data, because we're typing in all of the information, the sample means, etc. So the difficulty is that you have this 1 and this 2, so I'm going to put 1 for men, I'll put 2 for women. I don't mean to imply anything there. My apologies if I'm offending, but I'm just trying to keep things straight, and I have the left column, and I want to make sure that goes in the 1, so I keep it straight and I don't screw things up. So the x1 is going to be 67. The s sub x1 will be 2, and then my n1 is 25. The x2 is going to be 66. The s sub x2 will also be 2, and the n2 will be 25. Okay, now we're to the point where we have the not equals, we have the less than, and we have the greater than. All right, so I need to get to the greater than, and so I want to highlight that one. And then I'm going to go to the next one. It says pooled, yes or no. Well, the variances are equal. Since it says the variances are equal, we're going to hit yes on pooled, and then go ahead to calculate. And so we're going to get a t-score that's equal to 1.7677. And then the p-value is equal to 0.04. Now, statistics is one of these things, and I have to be careful with this because social statistics does a little bit differently than mathematical statistics. And so you get sort of this changing thing that goes on with social statistics. That's generally more challenging to deal with, so we're going to come at it from the mathematical perspective of a line in the sand. This is the line in the sand. We've gone beyond the line in the sand. This is landing about here. So this is my 1.7677. So it's a little bit farther out. It's in the reject the null region. Okay. Also, our p-value is smaller than our alpha. So if your p-value is smaller than your alpha, you reject the null. Okay, so step 1, we're going to reject the null. Okay, so I'm going to go back up to the null and put a line through it. That's no good. And this is what we're working with. We're saying that the mean height of men is higher than the mean height of women. Okay. Now, so reject the null. We give our level of significance. Alpha is 0.05. That's our second step. And then the third thing we do is we say something about the claim. Well, the data supports the claim that the mean height of men is larger than the mean height of women. So the thing you have to remember when I did my little drawing is that I'll try and bring the drawings back from above. So let me get here, let me go there. And you might be saying, well, yeah, but the standard deviations are the same. Why aren't they outside of each other? Well, here's the deal. Remember that the standard deviations are all getting adjusted by the square root of the sample size. And so what ends up happening is the standard deviation of 2 is getting adjusted by the square root of 25. So your standard deviations, which for an individual is 2, now the standard deviation for a sample mean of 25 is now adjusted by the square root of 25. So each standard deviation is now 2/5. And so when we start talking about standard deviations of 2/5, let me draw this. So we would put this standard deviation, here is your 67 inches, and our standard deviation used to be 2 inches, but now it's 2/5 of an inch. And so here's our 67, and I draw down here, and here's our 66, and if this distance is 1 inch from here to here, that's a distance of an inch. We're taking 2/5 of an inch. So 2/5 of an inch, well, we break it up into fifths. 2/5 of an inch is here. 2/5 of an inch is about, and I'm eyeballing it, so it'd be, let me see if I can get that fairly close. So I'm going to have 4 equal parts. So here, here, here. So 1, 2, 3, 4. So there's 2/5, or there's broken up into fifths, trying to match them. So a standard deviation is 2/5. So if I bring the distribution down this way, like so, well, 2/5. Okay, 1. So 1, 2. Ooh, I'm missing a tick mark, aren't I? My apologies. I need one more mark in there, so I'm just going to try and force a mark in there. I apologize for that. I missed that. So it's not balanced, but here's 2/5 going this way, and then another 2/5 going this way. So this value, where this mean is outside of 2 standard deviations away from this mean, and vice versa. So if I go 2 ticks this way and I go 2 ticks this way, then this mean is outside the 2 standard deviations. So it's far enough away to be captured by that too far away mark with standard deviations. My apologies for messing up the tick marks there. Anyhow, so our conclusion got erased. But the idea is that the t distribution is indicating that we are in the rejection region. Our p-value is smaller than our alpha, so that's telling us as well to reject. We rejected the null, so we put a line through the null, and then the alternative hypothesis supported. And because the claim is attached to the alternative hypothesis, the data is supporting the claim. Let me say it a different way. Because the claim is attached to the hypothesis that is being supported, then the claim is supported. I have a circle around this one. I have a circle around this one. If the claim had been on the null hypothesis, which it can be, depending on the wording, and you cross off the null hypothesis, then the word claim gets a line through it, and then you would not be supporting the claim. The claim would be rejected. All right. I'm going to stop the video there. Hopefully that makes sense.